Hey everybody, today we're going to start doing computations with limits at infinity. Um, we're going to do it by starting with a very simple function, y equals 1 over x, and using it as a foundation for our intuition into some much more complicated limits. So here we have a picture that we've seen before, y equals 1 over x, and you can see that as x goes to infinity or negative infinity, this function is going to 0. That makes sense because you've got a fraction where the denominator is getting bigger and bigger. You think about having a pie, splitting it into more and more and more pieces, the slices are going to have to get smaller and smaller. We can generalize this. We can take powers of the denominator, 1 over x squared, 1 over x to the 10th, 1 over x to the 1/5. As long as the power is positive, the denominator is still going to be growing without bound. And so the whole limit is going to go to 0, whether you're going to infinity or negative infinity. One tiny little comment here on that second line, x going to negative infinity, that'll only be defined if we're not taking, for example, a square root of x, x to the 1/2, or a fourth root of x, x to the 1/4. So that second line will be true as long as it's defined. For instance, the limit as x goes to infinity, 3 over the square root of x. You can think about factoring out the 3 to get 1 over the square root of x, and then viewing x as x to the 1/2. Overall, 3 times the limit x to infinity, 1 over x to the 1/2, which goes to 0 by the first line of the observation above. Let's do one that's a little more in depth. Limit as x goes to infinity, x squared minus 4x plus 1 over 2x squared minus x plus 8. So notice that the top and bottom are both quadratics. They're both like parabolas. And so both the top and the bottom are going to infinity. So the form of this thing is infinity over infinity. It's what we call an indeterminate. And literally it means we have not determined it yet. We've got some more work to do. When you've got a limit that's going to be an infinity over infinity, it could be huge, could be infinite if the numerator is going to infinity a lot faster. It could go to 0 or any constant in between. We have to figure it out. So we have this technique, we have this tool from the previous slide that we'd like to use. In order to make it work, we're going to do a little algebra. Here's the big idea. Find the highest power of x that there is in the denominator, and then divide that power out from both the numerator and the denominator. You divide it from both because whatever you do to the bottom, you want to do to the top so that you're not changing the function whose limit you're finding. Here, the highest power of x in the denominator is 2, so we're going to divide both the top and bottom by x squared. Dividing by x squared is the same thing as multiplying by 1 over x squared. That's why I've written limit as x goes to infinity, 1 over x squared, blah, 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 over 1 over x squared times blah, blah, blah. Then I distributed the 1 over x squared through. X squared over x squared is 1. 4x over x squared is 4 over x. And 1 times 1 over x squared is 1 over x squared. Similarly, the denominator becomes 2 minus 1 over x squared plus 8 over x squared. Now things get simpler because of what we had on the previous slide. 4 over x is going to 0. The denominator is going to infinity, the numerator is not. 1 over x squared goes to 0, same reason. 1 over x goes to 0, and 8 over x squared goes to 0. Everything is going to 0 here except the 1 in the numerator and the 2 in the denominator. Overall, the answer is 1/2.